Okay, so when a light bulb is conducting electricity, well, or when a light bulb is lit, it's basically conducting electricity, right? So in this case of it conducting electricity, we have the two electrodes that are touching. And so since the electrodes are touching, electrons are able to sit there and flow through this light bulb continuously, providing that electricity and providing us light. Soon as we disrupt that flow by separating those electrodes so they're no longer touching, we don't get light. So your light switch is basically doing it. So when you have your light switch on, it puts a bridge so that the electricity can flow through. And then when your light switch is off, it opens up that bridge so nothing can flow through. Okay, you see how that works?
Yeah.
Okay, so often we have been defining things that conduct electricity, right? So we know that metals conduct electricity, okay? So if we put a piece of metal between those two electrodes, we're gonna get electricity to be able to be conducted, okay? So the same thing happens with solutions. If our solutions have ionic charges in them, that plus and those minuses, it's able to conduct electricity. So an electrolyte are things that are able to conduct electricity. A non-electrolyte doesn't conduct electricity. So in this case, ethanol. Ethanol doesn't conduct electricity. So if we had electrodes sticking in solution of ethanol, like in the case of, can you guys see my figures? So
Yeah.
Okay. So if we have these two electrodes sitting into a solution of ethanol, and we connect that to a battery, we're not going to get any electricity conducted. Okay, but if we put in copper chloride, which will dissolve in water, right, in solution, and when it dissolves in water, it forms its ions. We have the copper 2+ ion, and we have the chlorine ion. And so since it's in water, these ions are separated because water is that home wrecker that causes these guys to break up. And then they're going solo YOLO, right? Then they're going to have their charges available, sit there and interact with the electrons. And then by them interacting with the electrons in solution, it allows those electrons to flow to the other side, and you get this nice flow of electrons. Okay, now a weak electrode doesn't dissociate completely. It partially dissociates. So if you kind of take a look here, I'm going to draw this out. So here, this is basically acetic acid when it's not dissociated. So the hydrogen is still attached to it. Now, when it dissociates, we get the acetate ion and we get the hydronium ion. And so you'll get this is your hydronium ion, and then this guy represents the acetate ion. But you only have a few of these. You only have like 2 of these compared to like you have these, I should say 1 or 2 of these, very few of them, compared to the number of acetic acid that are in solutions. So the acetic acid doesn't separate. And because it doesn't separate, you're not getting that plus and those minus charges that are going to allow it to conduct electricity well. So it's going to do it poorly because you have a few, but you don't have a lot. Does that make sense?
Yeah, it does.
Okay, so before we go, thank you for responding, Christy. Now, you guys know that this is a class, and you guys are already doing the black screen. So you guys have to also start responding a little bit to let me know that you're alive and you're not dead, and that you guys get it. Otherwise, I'll stay on the slide for a month. We're getting to that last leg. You guys know me, right? At this point, I want you guys to interact. You should be interacting. You should feel comfortable saying yes or no, I don't get it, right?
Yep.
Okay.
Yeah.
Yes.
Thank you. Okay, so electrodes are conductors of electrical charges, right? Those are those metal things that are sticking in there. Electrolysis is the process of electrons being conducted through those electrodes, okay? So when we actually look at it in a little more detail, so I told you that the water actually sits there and breaks up the ion. Not only does it do that, it kind of keeps it suspended in solution by the oxygens reacting with those positive charges, because we know that water is bipolar. It basically, it'll make that partially positive charge, which is on the hydrogen. That's going to be interacting with your negative charge. And then that partially negative charge is going to be interacting with the positive charge. So that means oxygen is going to be interacting with the positively charged ion, and then hydrogen is going to be orienting itself around the negatively charged ion, right? So like I said, water is like a home wrecker, right? It goes up to potassium in this case and says, hey, baby, you don't need chlorine. Come with me, right? And then it turns around the other side, and then hydrogen goes up to chlorine and says, hey, baby, you don't need potassium. Come with me, right? And it splits them up, keeps them in solution. And then because they're charged, electricity is able to sit there and capitalize on that. So it kind of orients itself towards the electrode. So your electrons flow through, so you get this negatively charged part here. So these positive charges are going to be shifting towards the negative, to that negative pole. And then your negative charge is going to be here, and it's going to interact with the positive charge, and then you're going to just get that bouncing of electron across there, right? And that bouncing allows that electron to sit there, flow through that solution.
Like opposites kind of attract.
Exactly, right? Remember we talked about that in the beginning.
Yeah.
Always have to go for that bad boy, right?
Yes.
Okay, so strong electrolytes basically dissolves almost completely. In other words, they ionize. Ionize basically means that they form ions, or they dissociate, or they dissolve, right? So they form that positive and negative. You have a lot of them in solution, right? A whole bunch of them. Where weak electrolytes, you only have a little bit in solution, right? So you get limited ionization or dissociation. And non-electrolytes will give you no dissociation, okay? Okay, so we were talking about those electrolytes. So how many of you guys drink Gatorade?
How many what? Sorry.
Drink Gatorade.
Out of the bottle.
Out of the bottle, yes. I'm talking about out of the bottle, yes.
I do.
I drink it.
Why do you drink Gatorade?
Yeah.
Hangovers.
At least she was honest.
That's what Pedialyte's for.
And Pedialyte. So what do you think? What are you getting out of those?
Electrolytes.
Electrolyte.
Electrolytes. Right?
Sodium.
Exactly. It's the sodium ions.
Sugar.
A lot of it is sodium. You have a little bit of magnesium. You have things as well. So
Potassium.
yep, and calcium. Okay. So in this chapter, we're going to be basically talking about that dissociation, right? So really what happens in solution, be down in a minute. Sorry. So in the case of like sodium chloride, salt, when we put it in water, what happens?
Dissolves.
It dissolves, right? So it dissolves and it breaks up into its ionic components. So really what's happening is that the water is separating the two, so those charges are available. And in the case, they're available for reactions if we have something that's going to be able to react with them, right? And I'll show you an image of it in a second. The same thing is going to happen with the dissociation of copper to chloride, right? So you're going to break up into your ionic components, okay? And these guys are going to completely dissociate. The only way that they won't completely dissociate is if you don't have enough water, right? So if we keep adding salt and salt and salt, we're going to get to a point where we reach saturation and we don't have enough water to cause that dissociation to occur, okay? Are you with me?
Yes, I get it.
Okay. Okay, so in solution, so here, this is the salt molecule as we stick it in initially. And then as time goes on and as we stir it or whatever, we cause those, the water molecules to basically surround the chlorine. So you'll have the oxygens are surrounding the chlorine. And then you'll have the hydrogens are surrounding the chlorines, the little white balls are the hydrogens. And the red balls are the oxygens, they're going to be surrounding the sodium. Okay, and so that's going to keep those charges suspended in solution. That's why salt doesn't fall out of solution unless you just keep adding a whole bunch more salt. Okay. Same thing is going to happen in the case of copper 2 chloride. So here's copper 2 chloride normally. As soon as we add it to the water, it's going to dissociate. Okay, and so it's a quick reaction. You're going to dissociate into your 2 ionic components. Okay, so this is called a dissociation reaction. Okay, or dissociation equation. Okay, so write the dissociation equation for potassium sulfate. Okay, so what's going to happen if we put potassium sulfate in water?
Gonna break up.
It's going to break up. Water's going to sweet talk it, right?
Yeah.
And we're going to end up with what 2 ions?
Potassium and SO4 by itself.
That's right. And we know that these guys are going to have charges. What is going to be the charge on potassium? Okay, somebody other. What was that?
Is it 1? Positive 1?
That's right. That's right. Okay. And since it's going to be in water, it's going to be aqueous. Okay. And the same thing, what about sulfate?
A -2 charge?
A -2 charge. And again, it's going to be aqueous. Okay. So like any chemical equation, we have to balance it out. So now you don't have the charges that are holding these guys together. So each of those potassiums are free to act independently. So in that case, we have 2 independently acting potassiums. So we'll put a 2 up here. Okay, you guys get that? And you see how that works?
Yeah, just break them up.
That's right.
Yeah.
Okay, so what happens in the case of calcium nitrate? Wilmer, what happens? Are you there, Wilmer? No, Wilmer? Destiny. Are you trying to talk, Wilmer? You may be on mute. Okay, Diana.
Can you repeat the question again?
So the question is, what happens in the case of calcium nitrate? Turn off those damn TVs. For telenovelas. This is the telenovela you should be watching.
Right. So Ca breaks up with NO3. Let's see.
Bad relationship.
NO3.
That's right.
It was toxic.
So they break up.
That's right. So we have Ca,
Charge of 2.
that's a 2 charge. Again, aqueous.
And then NO3 with a -1 charge.
And how many of those do we have?
So put a 2 in front of NO3. There you go.
Okay. Piece of cake?
Yep.
That one's easy.
Yes.
Okay. Okay. Okay, so the same thing happens with acid and base with acids. So as soon as an acid gets in solution, it's going to want to dissociate. The thing is that with an acid, that hydrogen ion it's going to actually become the hydronium ion. Because that hydrogen ion is kind of needy. And so it needs something to grab onto, right? So when it's with the acid, it's interacting with the nonmetal, right? And then soon as it's free, it's like going to try to grab onto something else, right? The first thing that it grabs onto is water because it's in the aqueous solution. So it forms the hydronium ion. So a lot of times we'll just depict it as this. We'll put an A with an AQ on it. That's the same thing as writing the hydronium ion with excess water. Okay, so they're often equivalent. Okay, so we know that H plus is a proton that's being donated. Okay, so the first thing that happens is, like I said, it'll dissociate and it'll interact with that water, and then whatever the conjugate base or the conjugate base, then it's gonna be alone, right? So it's gonna dissociate. So if we're talking about hydrochloric acid, then we get the hydronium ion and we get the chloride. Okay, so it's going to dissociate exactly the same way. So hydrogen is going to kind of act like metals in this case. So, and it's going to act like group 1 metals since it's lost that 1 electron. Okay, and so just like we saw with sodium chloride, it's going to dissociate when it's a solution. Okay, are you guys with me so far?
Yes.
Okay, so let's make it a little bit harder. I apologize for the slide. The next slide is screwed up. All my arrows are shifted. So when an acid is able to lose more than 1 H plus, more than 1 hydrogen ion, it's called polyprotic.
Oh, okay, sorry.
Polyprotic. Okay, polyprotic basically means, again, it's able to lose more than 1 hydrogen ion. So that means that it'll go through, it'll lose this very first one, and then later on, it'll go through and lose the next one. Okay, and again, I have to fix these slides. So this should be. And then this guy, is the arrow. You're gonna end up with this. Okay. So carbon-containing acids or carbon-based acids, these acids, they don't like to ionize, right? So they're not gonna ionize too well. So what happens is they form equilibrium. They form an equilibrium complex where the majority of the species are gonna be this, and then you're gonna have a little bit of this. So you're gonna have the existence of both, where these acids, these are strong acids. So strong acids are always gonna totally dissociate. Weak acids, you're gonna have more of your acid than your ions. Are you with me?
Can you say that again?
Repeat that again, Dr. Henry. The middle ones are the weak ones.
Okay, yeah, so carbon acids, anything that has carbon in it, carbon acids are weak acids. So what happens is they form what we call equilibrium. That means that they make a little bit of this guy. So this guy will be a little bit. But most of it is going to be this. And this is going to be most of it, right? So most of it is still going to have that hydrogen attached to, in this case, acetic or acetate. So you get mostly acetic acid in solution, and then you have very little of your hydronium ion and your acetate ion. So this guy's going to be a little bit there, but you're going to have both in solution. So soon as these guys come together, you're going to have another one that's going to dissociate, and that's considered equilibrium. You get to the point where you're not changing the total value; it's at a set type of value. Okay, does that make sense?
Yeah, it makes
The reaction is going both directions. Okay, so to recap again, strong acids ionized. So they're going to form a lot of ions, a whole lot of ions. So your major species are going to be your ions, okay? Now, your minor species is going to be the unionized molecule. It's going to be that acid solution, okay? So strong acids, an example of a strong acid is hydrochloric acid. So hydrochloric acid, when it's aqueous, when it's in water, it's going to dissociate completely. Okay, and it's going to form that hydronium ion or that hydrogen ion and your chlorine ion. So almost everything is going to be that way. So if you guys think about this arrow, the arrow basically means that you're pushing everything towards that product, okay? So if it's an arrow going both ways, that means that you have both things existing at the same time.
Like if you put water or heat or,
That's right. Yeah. So it's driving that reaction,
okay.
okay? Okay, so a weak acid is only going to ionize, it's only going to ionize a little bit in solution. So, and it's going to conduct electricity very poorly. The majority or the major species are going to be the unionized molecules, and then the minor species are going to be the ions. So often what we'll do to kind of help us understand it and visualize it is, let's say, again, we'll use acetate. Acetate is H2H3O2, or acetic acid. And what we'll do is you'll have a big arrow going in this direction, and then we'll have a small arrow going in that direction. Okay, so that lets us know that this guy is the major species, the one that exists most of the time. The problem is that when we're typing it, I don't have like a big arrow key and a little arrow key. Okay, so in this case, our major species is going to be the unionized molecule, where these guys are our ionized molecules, or ion. Okay, are you guys with me?
Yep.
Yes.
Okay, so just to recap one more time, I figure if I tell you like 20 million times, the same thing. Okay, so strong acids conduct electricity, right? And again, we have hydrochloric acid here. So we have the hydronium ion right here. And then we'll see that it's being surrounded by that water molecule. And then we have the chloride ion here. And again, it's being surrounded by the water molecule, but the hydrogens are facing it, keeping it in suspension. Okay, but you have all of these ions present in solution. So you're getting strong conduction of electricity. Here, this is the acetic acid. So this is an acetic acid molecule, acetic acid molecule, acetic acid molecule. Here we only have two of the ions present, right? So we have that the positive ion here and the negative ion here. Okay, so that's our acetate ion, and here's our hydronium ion. Okay, so in this case, because there's only a little bit of the ions present, we only get a little bit of conduction. Are you guys with me?
Yeah.
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 Okay. Okay, so we're actually going to stop right here after I go over it, so that you guys are still a little bit ahead of the other class, and I'll push the other class to catch up to you. So here's an example of a strong acid and a weak acid. So hydrochloric acid is a strong acid. So in the case of a strong acid, this is the chemical formula for a strong acid. These are the different molarities of the acids. And molarity is, it tells you the concentration of the HCl in that solution. So in a higher concentration, 79% of the HCl is ionized, and in a lower concentration, 99+% of it is ionized. Where hydrofluoric is a weak acid. Now, the reason why hydrofluoric is a weak acid is because fluorine, we've kind of talked about this, he's kind of like a bully, right? He's really strong, he beats his woman, he's that type of guy. And so he won't let hydrogen go. He's like, no, you can't go to the bathroom by yourself. No, I have to go with you, right? So he's always connected to hydrogen. He's not going to let her go unless he finds a better girlfriend, okay? So in that case, he's not going to let her go independently. He's always going to be there. She's always going to be right next to him, always attached, okay? And that's because the electronegativity of fluorine. Fluorine has a very strong electronegativity. It doesn't want to let go, okay? So because of that, you have very little ionization in solution. You have 9%. And then when you have a very, very weak or diluted solution, it's 22%, which is still really low compared to how much is non-ionized, okay? So this guy conducts electricity very well, the hydrochloric acid does, where the hydrofluoric acid doesn't. Now, the funny thing is that they're both in the same group, but because fluorine is so strong in terms of like electronegativity, it's not gonna let hydrogen go, where chlorine isn't as strong as fluorine. And so hydrogen is able to go as it pleases. Okay, are you guys good?
Yes.
Okay,
What'd you say?
so when we talk about those major species and those minor species, so the major species for that strong acid is going to be the ion. The minor species is going to be the molecule together, okay? Where in the case of the weak acid, the major species is going to be the acid, the molecule, and then the minor species is going to be the ions. Okay, so you got to remind me. I forget all the labs that I've given you, but I remember lab 9 is that's the balloon lab. Is that correct?
Yeah, that's correct.
Yeah.
Okay, so let's talk about, because you're trying to figure out. So you're talking about percent yield, right? That's what you're trying to find?
Yeah, I think that's what.
Okay.
Three.
Okay, so let's talk about what we're looking at. So when we're talking about theoretical, spell theoretical yield. Theoretical yield is what you actually calculate, okay? So you know how much stuff you're putting in there. So if you know how much stuff you're putting in there, you should be able to calculate how much stuff you're gonna make, right? Yes, no, maybe?
Yes.
Okay. So there we go. So in the case of the theoretical yield, we're given 1.5 grams of our sodium bicarbonate. Okay. Now, our chemical equation, we have Na, HCl, not HCl, HCO3, or sodium bicarbonate, is interacting with acetic acid, which is HC2, H3, O2. And we're going to make H2O plus CO2 plus sodium acetate. Okay, so I want you guys to take a look at this equation. Is it balanced?
Yes, it is balanced.
Okay, so we look at the equation, we know that there's a 1-to-1 ratio between the sodium bicarbonate and the carbon dioxide, right? So that lets us know quantity, right? So for every 1 molecule of sodium bicarbonate, I can make 1 molecule of carbon dioxide. Okay, so if I have my grams of my sodium bicarbonate, I need to change that to moles because I want quantity. When I'm using the chemical equation, I need to know the quantity, not the mass. So how can I change my mass into quantity? And what do I want to change it to?
Wait, where did we get 1.5 from again? I'm sorry.
Because that's how much the sodium bicarbonate weight, the very first
Yeah.
teaspoon that you have is 1.5 grams roughly.
So we do one for each of the, I think it's 5, right?
That's right. They're going to do it for
Or-
all
or
6.
6, right? Okay, cool.
Okay, so how would I do that? So I have 1.5. How would I change that to a quantity? What do I want to change it to?
Liters?
Is liters a quantity or is that volume? And volume.
You want to
is
get it to
space.
moles?
I want to change it to moles. That's right.
So you're going to
So-
put moles on top?
Okay. So moles of sodium bicarbonate. Okay, and then what's going to go on the bottom? How do I go from grams to moles?
You got to put grams at the bottom so it could cancel out.
Okay, so what am I going to use to calculate the grams at the bottom?
Is it 1?
So you're telling me that sodium bicarbonate weighs 1 gram per mole? I'm telling you, it's not 1. What am I going to use? There's a particular thing that we always look at, that we should always have next to us when we're working on chemistry.
The polyatomic ion?
Is that going to
So-
tell me? Is that going to tell me how to change grams to moles?
No, so
What was that?
Dimensional analysis.
Okay, we're going to use, that's a technique or a method, right? But what are we going to use? What tool do we use to determine? Oh my gosh, Brianna, where did you get that from? She has 84 in there.
Molar mass.
It's the molar mass. So we're going to use the molar mass, right? Because we want to go from mass to moles, molar mass, right? So where do we get the molar mass from?
List our elements.
From our periodic table, right? So we need to use our periodic table to sit there and determine our molar mass. Good job. Good job, Brianna. Okay, so then this gives us number of moles. Oops. Number of moles of sodium bicarbonate we have. Now we have a 1-to-1 ratio of moles of sodium bicarbonate to moles of carbon dioxide. So we're going to use the ratio in our chemical equation. So that's why we have to be sure that our chemical equation is balanced, because it'll let us know how much we can actually make theoretically, right? So we go 1 mole of our sodium bicarbonate to 1 mole of carbon dioxide. Okay, and so that gives me my moles of carbon dioxide. So I could calculate grams if I really wanted to, but moles is fine because I want quantity. Okay, so if we get our quantity here, what do you guys get? 0.0.
1.7 or 1.8.
Is that 218 or?
One 1785.
1, 7. Okay, so this would be my theoretical yield. Now my actual yield is going to be what I got from my experiment.
And the actual yield should be greater than the theoretical yield, correct?
Not necessarily. Okay, so it normally is lower than our theoretical yield, right? However, because we are using an estimate, this number here was an estimate. And so my teaspoon may be different than your teaspoon. Do you know what I'm saying? So
Yeah.
my teaspoon may be a little bit smaller than your teaspoon, and your teaspoon you may put a little bit more in, right? And so then it's going to change that value, but it was all based upon my teaspoon. Okay, so in our case, it's okay if our percent yield is greater than is greater than 100% because it's based upon my teaspoon. So I'm giving you that flexibility. Normally, you always come with a number that's a little bit less normally. Okay, so our actual yield is going to be what we calculate or what we get experimentally. Okay, so that's how we're using we were calculating the diameter of the balloon. You guys remember that? And so we did the calculation of the diameter of the balloon. Can somebody tell me their diameter? I think somebody got like 10 centimeters, something like that for the diameter.
I haven't done mine yet, so I can't. I'm gonna do it tonight.
You haven't done your balloon yet?
No, I'm gonna do it tonight.
Oh, okay.
One of the the greatest diameter, or it don't matter.
Let's do the smallest one first.
Okay, I had a 7.62 centimeters.
7.62.
Yeah.
Okay, so we got 7.62 centimeters for our diameter, right? So if we divide that by 2, because that's going to give us our radius. So
Wait, 7.62 or 7.2?
7.62.
Okay, I got it now. Okay, so this is going to give me my radius, right? My R, because it's diameter divided by 2. That's going to equal your radius. Okay, what do you guys get for that? What is that? 3.82. Okay, so my radius is 3.82. So then I'm going to use to calculate my volume of a sphere is going to be 4/3 pi r cubed. Okay, so then I'm just going to plug in my r value for there. So then I'll get 4/3 pi 3.82 centimeters and that's cubed. So then that's going to equal, so I get 2, 3, 3 centimeters cubed. Okay, so that's my volume, right? So I'm going to try to convert my volume into liters. How can I convert centimeters cubed into liters? So, anybody? 1 cc stat. Cubic centimeters. How many cubic centimeters are in a cubic meter? I mean, a cubic milliliter.
1.
1. So 1 cubic centimeters equals 1 cubic 1 cubic centimeters equals 1 milliliter. And then how many milliliters will equal a liter?
1,000.
Okay, so then we get 1,000 down here. Okay, so then I get a value of okay, are you guys with me so far?
Yes.
Okay, good. So we're going to use the ideal gas law, PV equals, or PV. PV equals nRT, and we're going to solve for N. N represents the number of moles. N equals number of moles. P equals pressure. We're going to assume that it's normal pressure or atmospheric pressure, which is 1 atmosphere. T is going to be temperature in Kelvin. Okay, we're assuming that it's room temperature. Room temperature is typically 23 degrees Celsius. So if I change that to Kelvin, I need to add it, what?
273.
73. Okay, so then that gives me what? 296.
96 Kelvin.
And R is the ideal gas constant. And that's going to be equal to 0.0821 ATM liters divided by moles Kelvin. Okay, so we plug all of these guys into our equation. So we had our volume, we just got, what was it? It was like, I don't remember. What was it? 0.23 or something like that, 33?
Yeah.
Okay, so I'm going to plug that into this equation, and then that's going to give me my number of moles. So I'll put 1 ATM times 0.233 liters over 0.0821. That's ATM liters over moles Kelvin. and 296 Kelvin. Okay, so my units, Kelvins are going to cancel out. The ATM liters are going to cancel out. And so I'll be just left with moles at the end. So that's going to give me my moles. So do that math. So I get 0.00. Oh crap. I forgot one thing, right? Wilmer, do you have a bottle? What bottle did you use? What type of bottle did you use for yours?
It was just one of those 500 milliliter regular water bottles.
Okay, so if it's a 500 milliliter regular water bottle, so then that's going to be 0.5 liters. I need to add that together. So that's from the bottle. Okay, because the gas is going to occupy the bottle as well as the balloon, right?
Oh, yeah, that, yeah.
Yeah, and this guy's from the balloon. Sorry about that. After we did all that hard work. Okay, so then that's 0.7 33.
Zero point zero 0.030. Is that what you got?
I got 0.3
Yeah.
like 0, yeah, 0.0 like 0.0301 or
Yeah.
2. Yep. Okay, so that would be the number of moles. So this would be my actual moles.
Oh my goodness. Okay.
Okay, so to calculate percent yield, it's going to equal actual divided by theoretical times 100. Okay, so my actual was this value. My theoretical, anybody remember my theoretical? I think it was like 0.
0.01785.
So 0.1785.
No, 0. I think it was 0.01785.
Okay.
Times 100. 169.
Oh, I forgot to multiply times 100. %. So 169%. So we're a little over.
Okay.
Okay. Does that help, Brianna?
That's for each.
He said no, thank you.
No, I haven't. What was that? Okay, go on. I need to finish. I'm working. Okay. Okay, any other questions?
And we do that for each one, right?
Yep, that's right. You do it for each one. So if you're smart, not to say that you're not smart if you did it individually, but if you're smart, you do it all in an Excel spreadsheet, and then you set up those calculations. Because all of these values are going to be the same all the time. The only thing that's going to be changing is your volume, right?
Okay.
So you'll set it up so it does all the calculations for you.
Okay.
Okay. Questions, concerns, Cash?
I was watching the lab video
Uh-huh.
and I saw that on the Excel, it had moles of sodium bicarbonate added to each reactant and then theoretical yield. It looks like they're the same number. So
Yeah, and the reason why they're going to be the same number is because it's a 1-to-1 ratio in the chemical equation. You take it back to the chemical equation.
so it should just still be there. I thought it was like I had two
Yeah.
in there.
Yeah, so they're going to be the same number. The number of moles of your sodium bicarbonate is going to be the exact same moles of your carbon dioxide because it's a 1-to-1 ratio. 1-to-1 ratio based upon the chemical equation. If it was a 1-to-2 ratio, then we would have to put 2 up here, and then it would be twice the amount that we would produce. Does that make sense?
It would be okay. So it would be the number of sodium bicarb times 2 or times if it was
Yeah,
doubled up or one.
so if the ratio, so I'm saying, now this is not the case here, okay?
Yeah.
So, but we're saying in a hypothetical situation, we're saying that we have a 2 here, right? So in that case, it would be for every 1 molecule of the sodium bicarbonate, we would end up with 2 molecules of our carbon dioxide. If we balance the equation and there was a 2 here. Okay, you got that?
Mhm.
That's not the case here. Okay. Any other questions?
Yeah, Dr. Henry, you're gonna go to your office hours right now?
Yes, I'm gonna go to my office hours right now.
Okay, could you put me and Christy in a group so we could talk to you in there?
Yes, that's fine. You can do that.
Okay, great, thanks. See you
Okay.
then.
I'll see you
So
guys
ju-
in my office hours.
So just to make sure, Dr. Henry, the actual yield does not have to be greater than theoretical, correct?
No, your actual yield, yeah, so your actual yield is typically not greater than your theoretical, but this just basically means that obviously there are issues with the problem, with our experiment. So we probably put too much sodium bicarbonate in initially. And so for that 1.5 grams, we probably exceed it more than that 1.5 grams.
Okay.
Okay.
Because I think I'm pretty much done, but I was told that the actual yield should be greater, so that I should be able
No.
to fix. I need to fix that in order to
No,
get
no.
that.
So typically the actual yield is less than the theoretical yield, typically. But if you use the yield to kind of help you figure out about your experiment, right? So your yield just lets you know how much you've made compared to what you're supposed to make, right? So 100% means you're perfect, right?
Yeah.
If you get 90%, that means that you're not quite perfect. But if you're getting 200%, that means there's probably something went wrong, or you probably put in too much. You probably doubled your reaction than what it was supposed to be.
Okay.
So that's what that typically means. So you use that yield to kind of let us know, kind of gauge it. Don't go quitting because of the yield. I told you guys my quitting story, right?
Yeah.
The limiting reagent is what we learned already, right?
Yes, you've learned the limiting reagent, yes, as well too. So the limiting reagent is where you learned remember we talked about the cheese sandwiches?
Yeah.
Okay.
Yes.
Where you had too much bread and not enough cheese for sandwiches or vice versa, right? So that's limiting reagent. Okay, anything else? Good, okay. So I will see you guys next week. Take your time on the exam. Again, nomenclature is the bread and butter. Make sure you know it like the back of your hand. Okay.